Drawing three-dimensional representations of these chiral molecules is awkward, difficult, tedious, especially when we have carbohydrates with multiple chiral centers. It just becomes really, really confusing. And so a scientist named Fischer came up with a great way to draw two-dimensionally these chiral centers. And so Fischer projections are a widely used way of representing chiral molecules, especially the carbohydrates. And so a Fischer projection is a two-dimensional notation showing the three-dimensional spatial arrangement around the chiral centers. So the way we do this is the chiral center is represented as the intersection of two lines. And so this would be the carbon atom in the center. And the Fischer projection is based on looking at a three-dimensional model, which I took mine apart, that was convenient, and putting it into two dimensions. So let's look at this three-dimensional illustration of a three-dimensional molecule. And one way to represent this in two dimensions is using hashed bonds and, wedge bonds and dashed lines. And so the convention is that the wedged lines are coming out of the screen at you. So the carbon atom is in the plane of the screen, and the X and the Y are like arms sticking out trying to hug you, right? And W and Z, the dashed lines, are going back. So the Fischer projection is like you take your three-dimensional model, you run over it with a steamroller. So you press it down flat. The W and the Z that were going behind the page or the screen are the vertical ones, and the X and the Y that were sticking out in front are the horizontal. So here we have the Fischer projection. And what we understand when we look at a Fischer projection is the vertical line is bending back and the horizontal line is coming out forward. And the way I think of it is I think of a person kind of bending backwards and sticking their arms out in front, like they're trying to grab you, right? So X and Y are someone's arms trying to grab you, but they're kind of bending back. Let's see if I can draw a picture. This should be good. So here you've got this guy, and he's got his arms out, right? And you can't really tell much from the front view, but if you look at the side, you see he's kind of leaning back, and his arms are sticking out in the front. That's my best way of remembering which one's sticking out and which one's sticking back. Somebody bending like this. Hopefully that won't give you nightmares. So if we look at the simplest monosaccharide with a chiral center, this is glyceraldehyde. And here we have its structure. So we have a 3-carbon chain, and here this is an aldehyde, and we've got 2 hydroxyl groups. So its other name is 2,3-dihydroxypropanol. And when we draw the Fischer projection for this, we always put the carbon chain vertically. So here's 1, 2, 3. There's the 3 carbons in the chain. The ones in the middle where the lines intersect are not specifically shown, but there's a carbon there where the lines intersect. We're also going to put the carbonyl group at the top. So for aldehydes, the carbonyl group is on the end carbon, and so that'll always be on the top. When we do ketones, we're going to put whichever end is closest with the ketone to be on the top. So if the ketone is on the second carbon, then that'll be at the top. So we're going to put our carbon chain here. Maybe let's throw some numbers in here just to help you visualize. So this is 1, 2, and 3. Here's carbon 1, 2, and 3. Carbon 1 is this aldehyde group. Carbon 2 has a hydrogen and a hydroxyl group, and carbon 3 has 2 hydrogens and a hydroxy group. This carbon is not chiral because it has 2 groups that are the same. Carbon 1 isn't chiral because it's got a multiple bond. Only the carbon in the center is chiral. Sometimes it's indicated with an asterisk. That's why there's an asterisk there, to say that that one's chiral. So here's our chiral carbon in the middle. And so there are 2 possibilities for how the hydroxyl group and the hydrogen group are. We can have this one on the left, or we can have the hydroxyl group on the right. And those will be mirror images of each other. And so if you want to visualize this in 3-dimensional space, we visualize this guy going behind the screen and this one going behind the screen, and the hydrogen and the hydroxyl group sticking out, kind of like arms. This is the mirror image. And we specify the images, or the enantiomers, with the letters L and D. L stands for levo, which is a Greek for left, and D is for dextro, which is Greek for right. So this is L-glyceraldehyde. And when we look at the Fischer projection, we're going to be looking at where is the hydroxy group on this carbon, this chiral carbon. It's on the left. So this is L-glyceraldehyde. It is convenient that at least L and left and levo both start with L. So that leaves D to be the other one, which must be right. So D-glyceraldehyde, the hydroxy group, is on the right. So we're going to draw them in this particular way with the carbonyl group as close to the top as possible, so we know which end is up, and the carbon chain is vertical. If, when you draw that, the hydroxyl group is on the right side, it's D. If it's on the left side, it's L. Here's another one. This one has 2 chiral centers, 2,3,4 trihydroxybutanol. Monosaccharide that has 4 carbons, 2 chiral centers. So here's its more familiar to us structural form. So these 2 carbons each have 4 groups attached to them. And this one has 4 stereoisomers. So all 4 of these are stereoisomers. These 2 are enantiomers of each other, because to be an enantiomeric pair, they have to be non-superimposable mirror images. This one is not a mirror image of that one. The nice thing about the Fischer projections is that the mirror image is, in 2 dimensions, is going to look like a mirror image. We're just swapping these. So on this one, the OHs are on the right side. On this one, the OH is on the left side. They're mirror images of each other. Over here, we've got one on the left and one on the right, and then the mirror image is with them in the opposite position. So these 2 are a pair. Enantiomers always come in pairs. There's 2 images, the original and the mirror image. So when we use the DL nomenclature, that refers to the highest number chiral center. So these are those same 4 stereoisomers, just with different things highlighted. When we number this carbon chain, we would start with the aldehyde group up here, the carbon. So that's 1, 2, 3, 4. This 4th carbon is not chiral. The 3rd carbon is the highest numbered chiral carbon. And so when we indicate whether this is a D isomer or an L isomer, we're looking at that carbon. In a Fischer projection, this ends up being the bottom one. So you're looking at the bottom one in this line. Is it on the right or on the left? Here the hydroxyl group's on the right, it's the D isomer. This is the L isomer, it's on the left. This is another pair. This is D, hydroxy's on the right, and this is L, here it is on the left. So what do we do about the chirality at the second carbon? Well, they take care of that by giving each pair a different common name. So this was, what was it, 2,3,4 trihydroxy butanal, I think was its name. Well, instead of using a name like that, they give it a common name. These guys are erythros. This is the D version and the L version. And these two are threos, the D and the L version. The IUPAC name for these, not considering the chirality, would be the same, because you have hydroxy groups on the same carbons, but they're oriented differently in space because of the chirality. Any questions? Let's draw some Fischer projections. So draw a Fischer projection for the enantiomer of each of the following monosaccharides. The enantiomer is the mirror image. So to draw the mirror image, I'm going to put the top and the bottom in the same, because those carbons are not chiral. They have no particular orientation that we have to worry about. And then this one has 3 chiral carbons down the middle. And I'm just going to mirror the other one. So the original has OH on carbon 2 on the left side, so I'm going to put it on the right side. So these are mirror images of each other. And then I'm going to do the same for the next one and for the last one. Okay? Now, which of these is the D isomer? What does D mean? The D means the bottom OH is on the right. So that would be this guy, right? This is the OH being on the right. So this is the D isomer, enantiomer, and this one will be the L isomer. And so I think of this guy as being multi-jointed, as curving backwards, and each of these is a pair of arms sticking out. It's kind of creepy, I suppose. Okay, let's do this one. Is this a ketone or an aldehyde? This is a ketone. Here's our carbonyl group, but it's not on the end. Remember, aldehydes and ketones take priority over alcohols, and so referring to this, they're all of these are alcohols. They've got hydroxy groups all over the place. But this is the important part. So this is a ketone. But drawing the Fischer projection of the mirror image of the enantiomer is very much the same. So there's that carbonyl group. This part is not chiral. It's just got the 2 chiral carbons in the middle there. Right here, that one and that one. Which direction we draw these doesn't matter, because there's a single bond here and there's rotation around the bond. So if you want to, you can draw these pointing over to the other side. But in reality, they just spin around. The part we're interested in is here at these chiral centers. So we're going to put not that. We're just going to do the opposite. So this one had both hydroxy groups on the left. This has both on the right. Here, this is a ketone. The carbonyl group is not at the top, but we draw it in the direction that the carbonyl group is closest to the top. Because here, this would be carbon 1, 2, 3, 4, 5. Yes?
So I missed this. The ketone moves. Does it matter which way?
It doesn't matter which way we draw it. We can draw the double bonded oxygen sticking out to the right or to the left because of the rotation around that bond. It doesn't matter. It's just at these chiral carbons where we have 4 different substituents that now direction becomes important. This one has a double bond, so it only has 3 different things, so there's no chirality. This carbon has 2 hydrogens that are the same, and that one, that's only 3 different groups, and so the orientation there doesn't matter. Like when I showed you the 2 models earlier, I had 2 chiral carbons and I showed you how they didn't superimpose, and then I took, I forget which color, but I made them so that each had 2 white balls and 2 different colored balls. And then I could take the mirror image and I could just turn it around and make it the same. That's the way all these other carbons are. So their orientation in space doesn't matter at all. It only matters for the chiral carbons. But here, this chiral carbon is on carbon number 2, and so we want that to be at the top. We're never going to draw it with this down here. And that's important because we have to always line them up the same way in order for the representation to be correct. So this is the L isomer, L enantiomer, because the hydroxyl group is on the left. For D and L, we're looking at the bottom chiral center, and this would be D because the hydroxyl group's on the right. Any other questions? Okay, so we've already been practicing this. Classify each as a D enantiomer or an L. So letter A, is that D or L? It's D, because the hydroxy group is on the right. How about B? That's L, because there we got the hydroxy group on the left. Characterize the following pairs as enantiomers, diastereomers, or neither enantiomers nor diastereomers. So remember, enantiomers are mirror images of each other, and diastereomers are they are stereoisomers that are not mirror images. Okay, so let's look at A. Here we've got an aldehyde, and we've got 3 chiral centers with all the hydroxy groups on the right side. Is this one a mirror image of that? No, it isn't. Is it connected all the same? There's a hydroxyl group on the 2nd carbon and the 3rd and the 4th. It's all connected the same, but they're not mirror images. That pair is a diastereomer. Diastereomer. How about B? What are those guys? These are enantiomers. All the OHs on the right versus all the OHs on the left. Enantiomers. How about this one on the bottom? Are they mirror images? This one's a mirror image, and this one is, but that part isn't, right? So they're not mirror images. Are they diastereomers? Are they connected the same? They are. When we look at carbon 1, that's the carbonyl group, carbon 2, hydroxyl group and hydrogen, 3, hydroxyl and hydrogen, 4, hydroxyl and hydrogen, 5 is the same. They've got the same things attached, but they're not mirror images, and so those are diastereomers. Diastereomers. Any questions? If you were doing our standard nomenclature from organic chemistry on these guys, do you see that they would all end up having the same name? See, this is 1, 2, 3, 4, 5. 5 carbons, so that would be pentanal, right? It's an aldehyde. And how many hydroxy groups are there? 1, 2, 3, 4. So it's tetrahydroxy. Oh, I don't have enough room for this. Tetrahydroxy. And those are on 2, 3, 4, 5. 2, 3, 4, 5. Tetrahydroxy pentanal. So really they're all the same. And if you looked at models of them, you'd have to really study and look at them to figure out, oh, I guess they aren't exactly the same. They're very, very much the same, and yet they're different. So here's another overview. It's even larger, showing again constitutional isomers. And there were 3 categories of that. Skeletal isomers, where the skeleton is going to be different. Positional isomers, where the position of the functional group is different. And then functional group isomers, where the functional group is actually a different functional group. Here's this one's an aldehyde, that one's a ketone. And then again another illustration of the different types of stereoisomers.